Okay, do you see my screen?
Yes.
Okay. So this is the second lecture about stochastic flows. My aim today is to finish the construction of a stochastic flow that we started last time, and then we will discuss some improvements, how to construct strong stochastic flows, and also look at some examples. So last time we worked in a locally compact separable metric space, and we considered three objects: a stochastic flow. To a stochastic flow, we associated a Feller convolution semigroup. To it, we associated a sequence of coalescing Feller transition functions, and then we came back. We constructed a Feller convolution semigroup from transition functions, and these objects are related as follows. So psi is a family of random measurable mappings of the space. Qt is a distribution of a random mapping that acts on the interval of length t, and pnt is an n-dimensional distribution of qt. So now let's close this circle and having a Feller convolution semigroup construct a stochastic flow. So the idea of construction is the following. D denotes the set of dyadic numbers. First, we will define random mappings psi st for s and t dyadic, and then by some approximation extend psi to all s and t. To do this, let me recall some objects that we introduced last time. So Zn is a dense set. P infinity, it is a distribution of a random sequence in M. So its first n components are distributed as P and T Z1 Zn. So this is a distribution of positions where Z1 Zn will go under our mapping from the flow. Also, we proved the existence of function L. So it is a measurable mapping from sequences in M into M, and it sends any relatively compact sequence into its limit point. I of y of x is defined as follows. So here it must be not z, but y. Let me try to. This is so y is some sequence, and x is a fixed point. So we define approximations nxk, yes, and as a result we get I of y. It is a measurable mapping of M. In this construction, I of y gives it sends zk to yk, and mapping j computes the value of phi at point zk. So Feller convolution semigroup was defined as the image of P infinity t under mapping I. Also, we have two properties: that J composition I is identity, and I composition J, it is a measurable presentation of Q. Okay. Now, let us consider a sequence of probability spaces. So the probability space with index n looks as follows. So it corresponds to countably many independent random sequences, each So these random sequences are indexed by the dyadic numbers of order 2 to the power minus n, and each this sequence is distributed as p infinity 2 to the minus n. It holds that if we substitute a random sequence omega ns into I, we will get a random measurable mapping with the distribution q to the power minus n, and intuitively it acts from s to s plus 2 to the minus n. Then let us consider mappings pi. So it takes a sequence of order n and produces sequence of order n minus 1 as follows. So first we act by mapping I from s to s plus 2 minus n, then from s plus 2 minus n to s plus 2 minus n minus 1, and we compute the values of this mapping at zk. And it turns out that under this mapping, probability Pn transforms into probability Pn minus 1. And it's quite easy to show because omega ns is distributed as I of omega ns is distributed as q 2 minus n. They are independent. So here we in fact have a convolution of q 2 minus n to minus n, and its image under mapping j. But then it is the q to the 2 to the minus n minus 1 image under mapping j. And since j composition I is identity, we get what we need. So now we have random mappings that act that act between all the dyadic numbers, and actually it holds that for this random mapping psi, we have the strong flow property. Okay, how we define psi st? We define when s and t are from one set dn, we define psi as a composition of the mappings that act between segments of length 2 to the power minus n. It turns out that the definition of psi doesn't depend on the choice of n, and for psi we have the strong flow property. So the fact that the definition is independent on n follows from our construction of inductive limit. Okay, and also now the flow property is easy to check. Okay, now let us approximate all other mappings, and recall from the last time that if we take independent sequences distributed as p infinity t1 tn and compose them using mapping I, we get the distribution q t1 plus tn. It follows that the law of psi is the needed one, and psi acts independently on disjoint intervals also by our construction. Now, if we look at the function which is a continuous function on m squared and vanishes at infinity, then expectation of f when we substitute psi into f is continuous in all variables st, u, v, x, and y. So here s less than t, u less than v, x, y belongs to m. And now st, u, v are dyadic numbers. This follows from the Feller property of transition functions. We can just consider three cases. Okay, if s less u less t less v, then psi st we can write as this composition, psi uv we write as this composition, and so first we apply v minus t to the second component. This is done by by this operator, then we apply t minus u to both components, and u minus s we apply to the first component. And we see that this expression is continuous. Okay. Actually, other cases are the same, and here, in order to apply Fubini theorem, we know that actually psi coincides with its measurable presentation by construction. Now fix t and define Tn as an increasing approximation of t by dyadic numbers, and psi st will be defined as a limiting probability of psi Sn Tn. This limit exists. Actually, it is uniform on compacts, which follows from lemma 2, and lemma 2 in turn follows from lemma 1, since we can approximate rho by some. So first, psi Sn Tn x, they are concentrated on the same compact with large probability. Yes, and there we can approximate we can truncate the distance function in a proper way. The constructed object psi is a stochastic flow that we need. Let's look at its flow property. So we need to show that psi su equals to the composition of psi st and measurable presentation of psi tu. Denote by xn the approximation of x, which is psi st of x. We know that xn converges to x in probability, and also we know the flow property for psi on dyadic numbers. Now, if we look at the probability that psi Sn un is at distance epsilon from this composition, we can rewrite it as follows. Yes, so here we use the flow property for psi Sn un, and the fact that psi Tn un coincides with its measurable presentation, and estimate this probability by adding and subtracting this psi tu of xn. And now, if so xn now is independent from psi Tn un and psi tu. So we can use Fubini theorem, and the first summand will go to 0. And xn converges to x in probability, and psi tu now is fixed. Last time we proved that in this case, also we will have convergence in probability. So a second summand also goes to 0, and we have the weak flow property. Now, let's discuss how we can improve weak flow property. We will say that a stochastic flow is strong if almost surely for all S, T, U, and X, we have the flow property. Interest in this question comes from one side, from the theory of random dynamical systems, because when you have a strong flow, it is very close to having a random dynamical system, and then you can discuss some invariant measures for stochastic flows, long-term behavior, and so on. And on the other hand, usually, well, not usually, but often you substitute random times in flow property, and you need to know that it holds.
Georgi, could you please explain us about measurability? Is it event, or do we assume that phi has nice properties with like continuous in X or Cadlag in S and U?
So here, I mean that outside the event of probability 0, this holds.
Okay.
So, but also we will construct modification with good properties in SU and X. The idea is the following. So if we take countably many trajectories from the stochastic flow, then we have the strong flow property for them. Yeah. So because when two trajectories meet, they must coalesce in the stochastic flow. So taking countably many trajectories, we will try to approximate rest trajectories and try to get a strong flow modification. We can change we can take an equivalent metric and assume that all bounded sets are relatively compact. Additionally, assumption is the continuity assumption. So here must be t to the power -1. Okay, so the probability that x during time t deviates from the initial position at distance epsilon goes to 0 faster than t, and it is uniformly over all compacts. Since I want to approximate trajectories by trajectories, I need a notion of some distance between trajectories. For this, I introduce the space of paths. So X, it is a union of all continuous functions, of all spaces of continuous functions. Yes, they start at all times, at all real times, and take values in M. If a function starts at time S, so I of f, it's the starting time, and also we can extend every function to R simply as a constant if t is less than s. Now let us consider this metric. Convergence in this metric means that initial times, that starting times converge, and trajectories converge uniformly on segments. Then with this metric, X is a complete separable metric space. Hence, in this space, we also have a measurable mapping that takes a sequence of trajectories and transforms it into one trajectory in such a way that a relatively compact sequence is transformed into its limit point. Now, I will use the following notation. If I have a sequence of continuous functions, by I of s, I denote indices of functions that started before time s. Okay, and a sequence phi will be called a skeleton if, so we have a coalescing property. This is the first one. So when two trajectories meet, then they move together. Sequence of starting times and starting positions is dense. And the third property means that we take any compact in the product and look at all functions that at time s they were in this compact. Okay, so we look at a function at time s, it arrives to a compact, and then we look at its restriction to it after this time. A function can start from this compact, then we look at all this function. So this this set must be relatively compact in X. By S of M, I denote the set of all skeletons, and it is a Borel subset of of space of sequences in X. The next result shows that any skeleton at every moment of time, values of functions from the skeleton are dense. Actually, it shows that if we fix S and S minus delta, then in any neighborhood, there will be a trajectory from the skeleton that at time S passed through this neighborhood and started between S and S, between S minus delta and S. The proof follows from the fact that the set of trajectories that started in a bounded set is relatively compact. So we can estimate its deviation and get the needed property. Okay. It turns out that we can construct a measurable mapping from R times M times space of skeletons into X. Yes, so it takes a skeleton phi, and to every point Sx, it associates some continuous trajectory in such a way that this trajectory starts at time S from X, and also this mapping preserves trajectories of the skeleton. It can be constructed as follows. Let us pick any sequence of measurable positive functions that at any point they decrease to 0, and organize approximation as we did in the construction of stochastic flow. So NSXK, it is the number of the first trajectory that at time S was close to X, close of order epsilon K of X. Then NSXK is some increasing sequence of integers, and I take this approximating trajectories after time S. Substitute this into our mapping L, and this is theta. Okay, so the sequence of approximations is relatively compact by our assumptions. So as a result, we will get its limiting point, which will be a continuous function that started from S from X at time S. Now, if X is already on the skeleton, then the sequence of approximations is stationary. So approximations have a limit, and we will get this limit. It is not necessary that NSXK equals to N. It may be equal to some N star, which is less than N, but phi N star and phi N are equal at time S. So actually, we have the needed property. So the measurable mapping theta takes a skeleton and constructs like a family of trajectories that started from all points Rn. And the trajectories of the skeleton are preserved. Okay. Now what I want to do, I want to take stochastic flow, to take a countable number of trajectories from this flow. Actually, I will take them starting from a dense set in R times M, and look at these trajectories as random variables in our space X. So the sequence will be a random element in a random sequence in X, and with probability 1 for all S less T, and we have the coalescing property. Also, we can show that with probability 1, the values of phi n that started before time t. They form a dense set in M. To show this, I will need the following strengthening of the continuity assumption. Here also must be t minus 1 times supremum, and well, it follows from our continuity assumption and the Markov property. Now, denote by omega AB the event that values of phi n are not dense at time t for some point t from A to B. Actually, this may not be an event. We will show that its upper probability is equal to 0. So if on this event values of phi n at time t, they miss some ball with center yi and some radius, let's say, to r. It follows that if a trajectory started like at time from t minus to delta to t and at distance r from y, then its deviation from initial position during time to delta will be at most r. Okay, now so since t belongs to the segment AB, we divide this segment into intervals of length delta, and we have the following property. So if we have Sn from one interval and the distance from xn to y is at least r, then the deviation from initial position will be at least r. And okay, where 1 is satisfied, I denote this event by omega delta JYR. But in fact, the probability of this event can be estimated. And since we consider segment AB, there can be only at most this number of segments J. Now it remains to take delta to 0 and apply the continuity assumption. So the random sequence phi, actually, we don't know whether it is a skeleton. So it obviously satisfies first two assumptions on the skeleton, but for the third one, it is not clear. So we will assume that it is satisfied. We assume that for any compact subset, the set of trajectories that at time s were in this compact is almost surely relatively compact in X. So we don't know whether we can deduce it from other assumptions on transition functions. But under this assumption, phi is a random skeleton. We can apply mapping theta to it and get some family of mappings. Will it be a modification of our stochastic flow? It depends on the choice of epsilon k. Recall that the function jk is upper semi-continuous, and I define epsilon k in the following way. So this is the infimum of r, such that the probability that distance between functions, distance between two processes, two trajectories from the flow is at least 2 minus k will be greater than 2 minus k. So if the distance between x and y is less than epsilon k of x, then this probability will be less than 2 to the minus, and we don't need it here. Okay, then this sequence converges uniformly to 0. Now, using this sequence, we get the mapping theta, and we substitute phi into it. As a result, the family theta, yes, which is defined here, is a measurable modification of psi. So it preserves trajectories of the initial of this big phi. Actually, all this was already shown for theta capital, except for medium. But the distance between phi k at time s and x is less than epsilon k of x. Okay, so the probability that the distance between psi s and phi k as a function is bigger than 2 to the power minus k is less than 2 to the power minus k, and we can apply Borel-Lemma. So almost surely phi k converges to psi, and our mapping theta chooses a limiting point of this sequence. So almost surely it will choose psi. In fact, similar constants show that theta almost surely preserves the flow property at stopping times. So now AT is a natural filtration of theta. Okay, we can define what is the stopping time, and when we fix s and x, then almost on the set when sigma is bigger and less than infinity, we have the flow property. Again, we look at so psi denotes theta as sigma of x, and we look at the approximation of theta. This is phi sigma xi k, yes, and here we need to use the strong Markov property. Okay. In fact, in some situations, theta can be a strong flow, and condition is that with probability 1, when s is strictly less than t, then after time t, the trajectory of theta coincides with phi n for some n. So it means that trajectories of theta, they immediately coalesce with the trajectories of the skeleton. Then it will be a strong flow because we know that theta preserves trajectories of the skeleton. And for this, a sufficient condition is the so-called instantaneous coalescence property. We say that a sequence of trajectories possesses this property if for all s less than t, values of trajectories at time t before time s form a locally finite set. It means that in each compact, there are only finitely many points of this set. If we assume that the skeleton possesses the instantaneous coalescence property, then theta is a strong flow. Actually, in this case, the condition of previous lemma holds, because if we denote theta stx by y, we know that it is a limit sum approximation phi ki, but in a neighborhood of y, there are only a finite set of values of phi. So this sequence of approximations simply must be equal to y for starting from some I0. So let's look for some sufficient now for the instantaneous coalescence property. These two conditions were proposed by Evans, Morris, and Sen, and well, in a slightly different way, because they considered only compact spaces. Now assume that for some compact we have a number of finite constants such that alpha kappa is bigger than 1, and we have the following two properties. The probability that two trajectories started from k at distance epsilon, and they stayed in k and did not meet during time proportional to epsilon to the power alpha. So this probability must be separated from 1. And the second property, it is the property of the space. We assume that if a set contains at least n elements, then some of them are at distance at most a distance proportional n to the power minus kappa. Denote by ASTK the set of so these are values at time t of trajectories that during time st they were in k. Then this set A is almost surely a finite set. How this can be proved? Assume that x, assume that we have a vector x, so it is n points, and at least k of them are different. Set epsilon to be proportional to k to the power minus kappa. Then by the Markov property, so among points x, there are two at distance at most epsilon. Yeah, so our assumptions imply that we have the following inequality. So here sigma n means that corresponding trajectories stayed in compact, and tau n k minus 1 is the time when there are at most k minus 1 of them. So if we iterate this inequality, we get such upper bound that allows to estimate the expectation of sigma n minimum tau n k minus 1. And the bound is proportional to k to the power 1 over k to the power kappa alpha. Taking the sums of such expectations, we can estimate the expectation of such stopping time. So this is sigma n minimum tau n m, where tau n m is the time when there are at most m trajectories. Okay, and So we will consider a series 1 over k to the power kappa alpha, which has this estimate. Now recall that kappa alpha is bigger than 1, and the estimate is uniform over all configurations in compact, and the estimate is uniform in N. So from this we can deduce that there cannot be infinitely many trajectories during some time. Okay. And since, okay, if the space M is compact, this already proves the ICP, but in locally compact setting, we need one more assumption. It looks like this. If we assume that we can cover M by compact sets, for which we have this instantaneous coalescing property, and every compact KK is contained in some compact KL, yes, such that if phi nt belongs to compact with index K, then then for some time it stays in a compact of with index L. Here R is independent from N, so this is really a condition. And since KL has the instantaneous coalescence property, we can deduce that phi possesses the ICP. These conditions are well suited to metric graphs. So a metric graph is a connected a metric space. So it has vertices, edges, and we assume that every vertex has finite number of adjacent edges. Well, metric graphs look like this. And also, we will consider simple neighborhoods of points in a metric graph. So this is just a union of segments around V. Yes? And every segment is on belongs to an adjacent edge. Okay. For metric graphs, it turns out that we can forget about the last property from the definition of the skeleton. So as soon as phi possesses the instantaneous coalescence property, then it is almost surely a skeleton. For this, we need to check that this relative compactness assumption. Actually, what I'm doing is the following. We look at we look at some simple neighborhood like this. And by denseness property, we can find trajectories in the skeleton that they moved above this the segments from simple neighborhood. It means that at every time when we consider these trajectories, they itself form a neighborhood of a point. And since we have the instantaneous coalescence property, there can be only finitely many trajectories that started before time some. If this is at time t, this is at time, say, t minus delta, and this it means that if a trajectory starts before time, okay, so it means that if trajectory is at time t minus delta in this simple neighborhood, it must coalesce with the one of the trajectories that are denoted by red points. And since there are only finitely many such trajectories, they will be uniformly equicontinuous. And then there are some technical considerations, but maybe I will skip them so we can cover the compact by finitely many such neighborhoods and prove the needed property. Okay, and the condition of Evans, Morris, and Sen for metric graphs look like this. Kappa is 1 and alpha is 2. So why kappa is equal to 1 must be clear, because locally a metric graph is like a union of segments, and it means that any alpha which is bigger than 1 suffices. So we will consider this condition with alpha equal to 2. And there is a class of processes for which this condition can be verified. These are Walsh-Brownian motions. These processes behave in the following way. So we have some metric graph. And to each vertex, we associate probabilities with which the motion will choose to which the direction it will go. On each edge, it moves like a Brownian motion, and at each vertex, it randomly chooses the direction of motion according to associated probabilities. And we are interested in an analog of Untitled flow, but for metric graph. So we will show that there exists a strong stochastic flow whose trajectories are independent Walsh-Brownian motions before meeting, okay, and when they meet, they coalesce. We need to check the inequality, this inequality for any simple neighborhood. It means that it is enough to consider a situation when actually we have only one vertex and some adjacent edges. Since we will look at the probability that two independent Walsh-Brownian motions will not leave this set and not coalesce, it is enough. Actually, we then can extend these edges to infinity and look at the Walsh-Brownian motions on this so-called star graph, and estimate the probability that they coalesce before time proportional to distance squared, and estimate this probability uniformly from above. So when if we do this, we will prove what we need. Okay. And now let's consider several cases. So assume that one of the Brownian motions starts at 0. It is known that Walsh-Brownian motion is scaling invariant. So actually the probability, the written probability is equivalent to the probability that one motion is at 0, second one starts at distance 1, and they meet before some fixed time. But it is easy to see that this probability is bigger than 0, because once these trajectories will be on the same edge, and then there is a positive probability that independent Brownian motions meet before hitting zero. Hence, we proved that for any beta bigger than zero, there is P which bounds this probability from below. So second case, when starting points belong to different edges. In this case, the distance between them is the sum of absolute values, denoted by tau y, the time when y hits zero, and we can estimate the probability of meeting as follows. Yes, so we estimated from below by the probability that y hits zero before time y squared. At this time, x is at a distance x plus y from zero, and they coalesce before time x plus y squared. Use the strong Markov property, and we know that on this event, when x is less than x plus y, processes meet not faster than the process that started from a distance x plus y. Okay, and we get a uniform estimate from below. So this probability is estimated, and to estimate the remaining part, we use this inequality and scaling property for y. And here everything combines, and we get again the needed estimate. And when two processes start from the same edge, it's a bit more complicated. We can let us first denote by Q the probability that independent Brownian motions started at distance 1 meet before time 1. Choose epsilon in such a way that this equality holds. Okay, and now let's consider x and y. So they belong to the same edge. We assume that y is less than x, so the distance is the difference. Using scaling property with r equal to x over y, we can write the probability as follows. Now, I estimate this probability by the probability that processes meet before time r minus 1 squared, and during this time y didn't hit zero. Then I can replace them with usual Brownian motions and get the following estimate. Now here the first expression is exactly Q, and the second expression is bounded by Q over 2. Because, no, so first we write it using the reflection principle, and if r is less than epsilon, is less than 1 plus epsilon, then we get a bound Q over 2. Okay, if r is bigger than 1 plus epsilon, then we can actually proceed as in the case 2. So same estimates work. Okay, so this is an example of strong stochastic flow, or strong coalescing stochastic flow on metric graph. Now, maybe I will take a few minutes, and I have some time or not?
Yes, yes, you have.
Okay. Now, what if the skeleton phi doesn't possess the instantaneous coalescence property? In this case, theta may not be a strong flow, so we look more precisely at points where the flow property can fail. Define the set of exceptional points as follows. This is the set of points Sx such that immediately after S there is a possibility to branch for trajectories. So outside the set E, actually we can prove the strong flow property for theta. Now, the idea is if there are exceptional points, when our flow hits exceptional point, we will reconstruct its trajectory so that we get a flow property. However, hitting set E, it can be a complicated event. So instead of hitting set E, we will consider times when we hit its closed shell. It is a closed set that contains E with probability 1. So sigma is this hitting time, and let me define psi as follows. Before time sigma, it is just theta, and at time sigma, okay, so we take the value at time sigma and apply theta to this value. It turns out that psi is a measurable modification of theta, and also it preserves the trajectories of the skeleton. It is a modification of theta because of the lemma, yes, that at stopping times, theta has the flow property. Now, assume that if the heating was after time S, then we must arrive to the skeleton at time sigma. And if sigma is equal to S, it means that we hit F in any neighborhood of so immediately after start we hit set F. In this case, we must have the coalescing with the trajectory of the skeleton, and under these two conditions, psi is a strong flow. So the verification it separates in several quite easy cases. Let us know that if we have the instantaneous coalescing property, then we can just take the whole space to be the closed shell of E. Okay, and finally, this is an example. The coalescing Tanaka flow. So the Tanaka equation, it is known that it has no strong solution. So we define endpoint motions as coalescing solutions to the Tanaka equation. They have the relative compactness property because the increment of every trajectory, either it follows B or minus B. So, and the flow looks like this. So we have parallel motion before hitting 0, and after hitting 0, we also, so something happens. We start choosing excursions of B, but the main property is that when the upper trajectory comes to 0, all trajectories below, they also go to 0. And since we have a dense set of points from which we choose trajectories in the skeleton, they will also go to 0. So in this case, at the closed shell, we take R times 0, and this is an example of a strong flow that combines the coalescing effect, and also it has a the maps actually are smooth outside some set. Actually, maps are linear, yes, for large values of x. Okay, maybe I can stop here and thank you for the attention.
Thank you very much. Georgi, can I ask you the question about this work of Evans and Coalescence, where they introduced conditions for instantaneous coalescent property? They considered, as I understood, the compact.
Yes.
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 And after any positive time t, we can guarantee that we have only finite number of points.
Yes.
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 Do they consider the asymptotic of this number when t goes to 0? Because it can be interesting question related both to structure of the compact and to properties of the one-dimensional Markov processes.
As I remember, no. So this work is considered only with the construction of instantaneously coalescing trajectories. They apply it to some fractal sets because the condition has this fractal nature. So, they have a locally compact setting, but they a very special one, and they don't extend their method, but they invent something new to it.
Yeah, it seems that it can be very interesting, like in the paper of Shamov, of our paper with Lovchansky and Minedin, to understand the asymptotic of the number, at least of the number of clusters and so on. Okay. Some other questions, please.
And I have one more question about same topic. Is it possible to, so are there examples of multidimensional diffusions with this Evans property?
I'm sorry, I didn't hear.
What about examples of properties that we discussed from Evans' paper in multidimensional case?
I
didn't hear the question.
Maybe I can repeat because I hear the question of Pilipenko. He asked about multidimensional diffusions as an example of Evans' picture. Do they have some multidimensional examples?
In Evans?
Yes.
They have examples in spaces with fractal dimension.
So we have to relate properties of diffusion and properties of the space.
Yes, it is their condition that alpha kappa is bigger than 1. So alpha is how fast we coalesce, and kappa is related to the geometry of the space.
Okay. Andrei, did you hear the answer?
Yes.
Okay. Yeah, I'm like translator.
But I didn't hear the question.
Okay. Maybe some other questions, please. Okay, if there are no questions, thank you again for interesting topic and good explanation about it. And we will meet one another after